we're going to take a look at an example where we practice calculating the standard error, the test statistic, and a p-value for a hypothesis testing problem involving two population proportions. Now, I'm going to preface this video by saying this is not the primary method that I'm going to be asking you to use to solve these types of problems. It is a little tricky. We just need to be very careful with our calculations. They do tend to be very touchy. So we want to be just very, very careful with the way that we enter our data into our calculator, because any amount of rounding that we do in the middle is going to introduce some error, some mistake into our problem. And then as we work with that more and more, that mistake gets worse and worse. So we want to try to not round any of these numbers until the very end of our problem, which means we've got these big, long, ugly decimals along the way. So we had said in the last one, the question that we're looking at here, it says, is there a difference between the proportion of all Duke students and the proportion of all U.S. adults that would be bothered a great deal by the melting of the northern ice cap? So last time we said we were going to call U.S. adults, we were going to call that population 1, and then Duke students, we were going to call that population 2. So if I'm going to start off, I need to find the standard error. I need to start by looking at p-hat pooled. Now, we calculated that in the last video, but just to kind of recall what that looks like, remember p-hat pooled is x1 plus x2 divided by n1 plus n2. I'm essentially going to pool my two samples together and treat it as one big giant sample. So I want to take the number of folks from both samples that said that they would be bothered a great deal, add those together, that's going to be my numerator, and then I'll do the same thing with my sample sizes, that's going to be my denominator. So it should look like 454 plus 69 divided by 680 plus 105, and if memory serves, we ended up with 0.6662 as our p-hat. So we're going to have that before we can do anything else. The other thing that will be helpful for us eventually is we are going to want to know the separate sample proportion. So what's the proportion of U.S. adults that said that they would be bothered a great deal, and the proportion of Duke students. Now, I'm going to call that p-hat 1 and p-hat 2, but occasionally you may see me in videos say, okay, well, that's going to be p-hat sub U.S. for adults, or U.S. adults, and p-hat sub D for Duke. You can notate these however you want. I will usually use this US and Duke or US and D just to kind of help me keep track of which one is which. It's totally up to you how you want to notate it, though, as long as you know which one is which and as long as it's clear to me as I'm reading through your work and whatnot. So we're going to look at, we said, p-hat 1 and p-hat 2, just to be consistent with the formulas that we're going to see in just a second. P-hat 1 is the proportion of U.S. adults that would be bothered a great deal, which is 454 divided by 680. So let me grab my calculator real quick. 454 divided by 680. I ended up with 0.6676, and then p-hat 2, the proportion of Duke students that said that they would be bothered a great deal. That's going to be 69 out of 105. So 69 divided by 105 gives me 0.6571. So all of this is information that's going to come in handy. The other thing that we might want to make a quick note of is N1 and N2. Remember, those are our sample sizes. So N1 will be the sample size from the U.S. adults groups, and N2 will be the sample size from the Duke students group. So I'm going to write down the formulas as we need them just so we can see what they look like. But if you need to pause the video to copy those down or reference the notes above, please do that. I'm going to start off by finding my standard error. So my standard error, this is the most mechanically difficult just because there's a lot here. There's a lot of calculations. So standard error says square root of p-hat times 1 minus p-hat divided by n1 plus p hat times 1 minus p hat divided by n2. So I have a lot of calculation to do. I'm going to go ahead and just take my p hat, my n1 and n2. We're going to start by plugging those into our standard error formula. So we have square root of p hat 0.6662 times 1 minus 0.6662 divided by n1 is, we said, 680 plus p hat, once again, 0.6662 times 1 minus 0.6662, make sure that's under the radical, divided by n2, our sample size from Duke students, which we said was 105. And then after that, it's just a matter of performing this calculation. Now, this is pretty tricky because there's a lot of decimals. There's a lot of moving parts here. So usually what I'll recommend doing is I'm going to calculate just this part first, and I'm going to try and work my way from the outside in. So I'm going to look at that part first, and then I'm going to go ahead and add this fraction next. And then once I've added those two things, the only thing left to do is to take the square root of the result. So I'm going to take 0.6662 times 1 minus 0.6662, and then divide that by 680. And if you look at your calculator right now, mine's telling me 3.27 e negative 4, right? That's 3.27 times 10 to the negative fourth. It's a very, very small decimal, so it's very difficult to write this out in the intermediate steps. I probably wouldn't even recommend doing that. But I'm going to go ahead and say I'm going to add on 0.6662 times 1 minus 0.6662 divided by this time 105. And I'll get a slightly bigger decimal. This time my calculator's not giving me scientific notation. It says 0.0024. So we could round it here if we wanted to, but again, that's going to introduce some amount of error. We want to be as exact as possible when we're working with these. So I'm going to take the square root of that big, long, ugly decimal, and if I've done my work correctly, I end up with 0.0494. I'm going to round to 4 decimal places just to be safe. So this is my standard error. I would encourage you to pause the video and try to perform this calculation on your own and just make sure that you get the same number. And if you have trouble with your calculator, you're not getting quite the same thing that I am, reach out to me and we'll talk and we'll figure out what's going on. But I ended up with a standard error of 0.0494. So there's the first part of my answer. The next part, if I'm going to do a hypothesis test, I need to know what my test statistic is. So for the test statistic, my test stat, so because we're working with proportions, my test statistic will still be a z-score. As we'll see in other types of hypothesis tests, it's not always going to be a z-score, but for right now it is. That's good. That's something we're used to working with here. My z-score, my test statistic, looks like p hat 1 minus p hat 2 divided by our standard error. So I need to go back and find what I said p hat 1 and p hat 2 were. So scrolling back up here, we said p hat 1 was 0.6676. So let's go ahead and write that down. 0.6676 minus p hat 2. Let's go take a look there. P hat 2 we said was 0.6571, so minus 0.6571 divided by our standard error, that's what we just found last time, 0.0494. So let's go ahead and calculate this out. So let's see, 0.6676 minus 0.6571 divided by our standard error, we have 0.0494, and here I end up with a positive 0.21. If it's a z-score, I only need 2 decimal places. So we'll go ahead and leave that as z equals 0.21. So this is my test statistic, and I want to point out right now that the reason why we don't want to round in the middle of these problems is if I had rounded, let's say, at this step right here, then that means that when I plug this in, when I take the square root, the actual standard error itself is going to be a little bit off due to the rounding that we did. And because these numbers are such small decimals, any amount of rounding is going to have a large impact on our answer. So that means when we take the square root, we're going to get something different. And then at the end, my test statistic also needs my standard error. So that means that that number is going to be a little bit different. So it says z is equal to 0.21 here. So we have our standard error. We have our test statistic. What was our last part right here? We were asked to find the p-value here. Now, in order to find the p-value, this is a step that we skipped over here. We need to talk about the null and alternative hypotheses. That's something that we talked about earlier on in the pages, but just to kind of reemphasize that the claim that we are testing here is there a difference in the proportion? It's not saying that one of these is greater than. It's not saying that one of these is less than. It's just saying, is there a difference? So technically, I really should have done this at the beginning of our problem. When we set up our null hypothesis is always P1 is equal to P2. Or if you want to simplify and say P sub US is equal to P sub Duke, so we're talking about the proportion of U.S. adults that would be bothered a great deal by the northern ice cap and the proportion of Duke students that are bothered a great deal by the northern ice cap melting. So we're comparing these two proportions. That's my null hypothesis, and the nice thing about this is that the null hypothesis is always, always, always the same. So I've got H naught. HA, we said the key word here that I'm looking at is there a difference? Is there a difference between, meaning this is going to be a two-tailed test. So that means that my alternative hypothesis will be P1 is not equal to P2, or if you prefer the other notation, P sub US is not equal to P sub Duke. In any case, really the one thing that I need here is the type of test we're doing. And in this case, we're doing a two-tailed test. That part's important because that's going to determine how I think about my p-value. So, scrolling down to think about our p-value here, we said a two-tailed test from our alternative hypothesis. So that means when I set this up, I have two tails to consider. On the one hand, I have positive 0.21 as my z-score, and I want to find the area to the right of that. That will be part of my p-value. On the other hand, I know that the area to the left of negative 0.21 will make up the other part of my p-value. I would like to find the area in these two tails and add them together. Remember, what's nice about the normal curve is that it's symmetric, so if I get one of these, I'll get the other one for free. These two areas are identical, so as soon as I find one, I'm going to find the other. So I'm going to look for the area to the left of negative 0.21 just because my z-table always tells me the area to the left of a z-score. So let's go look up negative 0.21 in our z-table. So swapping over to my z-table, we said we wanted z equals negative 0.21. So let's see if we can find that. I might have to zoom out just a little bit here. So I'm looking down here at the bottom. Here is negative 0.2. So this is the row that I'm looking at. And then the column here, looking across the top here, is 0.01 is my second decimal. So that means I'm looking at 0.4168. So I suppose half of my p-value is 0.4168. So let's hop back over and say, okay, this area is 0.4168, but I know because of symmetry, that also means that this area right here, this area right here is also 0.4168. I'm going to go ahead and add those two together, or you could also just multiply it by 2. And I end up with a p-value of 0.8336. This is our p-value. So as you can see, this was a lot of work. It's a lot of calculation, and it's a lot of delicate calculation where we don't want to be rounding. We're having to work with these big, ugly decimals. And that's why primarily I'm going to encourage you to use a graphing calculator to answer these types of hypothesis testing questions.